In this video, we will look at yet another method for solving initial value problems, which is the midpoint method. Now, the midpoint method has an approach which is quite similar to modified Euler in that it tries to account for the fact that f is changing over the interval from I to I plus 1, and that it tries to incorporate this change by not only looking into information on f from step I or from step I plus 1, but maybe trying to get somewhat better information on f. Now, in modified Euler, what we did was we take a full Euler step as this preliminary approximation here, and then we use this y star only to approximate or only to compute the slope in the point xi plus 1 y star, such that we can average out these two slopes in order to update the actual numerical solution that we're using. Now, in midpoint rule, or the midpoint method for solving ODEs, well, the approach is very similar, but instead of taking a full Euler step here, well, what we do is we take a half Euler step using the current slope at current step I. So we take a step with half width, h over 2, and then we use the slope at this midpoint in between point I and point I plus 1. We use the slope at that midpoint in order to update the solution in the next step. So let's take a look at what this looks like in a practical example. So again, here we revisit our initial example. It's getting very similar right now to what we've seen before, but this is the ordinary differential equation, the initial condition, the exact solution, and let's walk through the midpoint method for solving this initial value problem. So the midpoint method first computes a midpoint in between here, x1 and x2. It computes the midpoint, and then it will try to evaluate the direction field at the midpoint in order to really update the numerical solution for the next step. So the first thing we do is, well, we try to compute, we compute the slope based on f at x1 and y1. So that is this, again, this horizontal line. And then we find xm in between x1 and x2. So that's here at x is 0.2 for h is 0.4. So that's at 0.2. And then the y at that midpoint, well, that's the previous y coordinate plus the half width times the slope, so that's equal to this green star over here. That's the midpoint, and that's where we will then again evaluate the direction field, so the function f, or the right hand side here. So here we evaluate x times y, and this will give us a slope with which we will actually update the solution. So that's how it works. So we then find the slope at this point, we draw a line with that slope from the current solution, and then we find the new solution to be here. And again, we repeat this procedure. So we draw out a slope, a line based on the current slope at x2 and y2. We identify this midpoint over here using these two formulas, and then we evaluate the slope at the midpoint. We draw a line corresponding to the slope at the midpoint, and then our new solution will be where this line crosses x is equal to x3. So that will be over there. And we repeat this procedure. So find the midpoint, evaluate the slope, update the solution. Find the midpoint, evaluate the slope, update the solution, and we continue to do so until we reach the end of the interval. So comparing the methods that we've seen so far. So we've looked at explicit Euler and implicit Euler for this problem, both of which were first order. And we see that for an h of 0.4, so all the numerical methods here are with h of 0.4, they are off by quite a bit. Whereas both modified Euler and midpoint are much closer to the exact solution. And also this goes without proof in these lectures, but you can rest assured that midpoint is also of second order accuracy, so that is also practically much more usable than explicit or implicit Euler.